right. Oop, wrong one. All right. So welcome to the Earth Science Education Hour. We are part of NESTA and we like to build, learn, and explore. And we are here for all the Earth Science teachers. Okay. If you are interested in joining NESTA, if you're not a member, we do offer a lot of opportunities like this education hour. We also give access to the journal, The Earth Scientist, with a monthly e-newsletter, community feedback, and lots of networking and people who can really help you in whatever you're looking for. Okay. Okay. For this month, we have our hands-on science with a DIYnamics team. And at this point, I am going to hand it off to our presenters, John, Bill, and Jordyn over here. And you guys can take it away now.
Hi there, I'm John Arno. I'm a geophysicist in the Department of Earth, Planetary and Space Sciences at UCLA, and we do a lot of rotating fluid dynamics of planets and stars. And we've made these hands-on kits that we're going to talk about today and show you some of the experiments we can do. Sai, you want to do it while we're on my...
I am one of John's grad students. I work on experiments of rotating convection.
Absolutely.
And my name is Bill Church. I'm a former high school physics teacher, and then I worked extensively in the nonprofit world doing STEM outreach support. A longtime friend and colleague with John Arno, and a few years ago had a chance to jump on the DIYnamics team and start helping out with the kits that we use.
And hi, everybody. I'm Jordyn Moscoso. I am an environmental scientist at SFEI, which is the San Francisco Estuary Institute. And my work centers on connecting science to policy. And so I run the model of the San Francisco Bay that gets used to make decisions at the State Water Board. And so I'm going to share my screen real fast. Oh yeah, in my previous life, I was also at UCLA, which is how I started with DIYnamics. We good? Fabulous. All right. So just to get started, I'm going to go through a few slides that talks a little bit about DIYnamics and about what we're going to be presenting today. And so we'll just get started with that. So quickly about us, we are the DIYnamics team. Do-it-yourself dynamics is the full name. And our primary focus is to help teachers build hands-on exploration with students for ocean, atmosphere, and space science topics. And we do this with our DIYnamics kits, which are down here, and you'll see a lot more of those as the webinar goes on. And these are turntables that are driven by Legos that allow us to simulate ocean, atmosphere, and other like space and planetary processes. And in this webinar, we're going to focus on storm systems that lead to atmospheric rivers. So the kind of broad outline is an introduction that we're in right now. And then after I'm done with this quick intro, Bill is going to give us a live build of our Lego motor. So just kind of show how easy it is to put these together. And then John and Sai are going to run an experiment with atmospheric rivers. Okay, so in this intro, what we'll do is we'll talk about how the system itself, like the Earth itself, and how atmospheric rivers form, these large storm systems that lead to atmospheric rivers. I'll go give a brief overview of like all the dynamics behind the systems, and then we'll talk about how to build our system and then how it relates to NGSS. Okay. So first, let's get oriented and talk about what atmospheric rivers are. You're looking here at a map of the Pacific Ocean off the US West Coast, which is in here behind this like opaque figure. The colors overlaid on the globe show total atmospheric moisture, but you can think of this as potential rainfall. The darker blue colors have higher potential rainfall and the lighter colors have less. And what you can see from this figure is this really, really long band of dark blue here, and this is what we call an atmospheric river. Atmospheric rivers are really long and narrow regions of concentrated moisture in the atmosphere, and they're called rivers because they carry a massive amount of water from the tropical Pacific to the US West Coast. Some estimates say that they're about 7 to 15 times the flow of the Mississippi River, which is massive, and these things have major implications to global weather. And so, you're thinking about these big global systems, and the real question is can we actually see something that is so massive in nature, like across half the size of the Pacific in our student setups that sit on a desk? And the answer is yes, we can. And we'll get more into details about how we do this as we move forward, but the photo on the right shows the setup of our atmospheric river experiment that John will do and in one of our DIYnamics kits. And what you can see here is a very similar type of structure where you have this long elongated stretch of this like purpley reddish color here, which is just like the atmospheric river that we see on the left. Okay, so there are first a few things that we need to understand about how these things form on Earth to get them to form in our takes. So let's walk through that real quickly. So here's a picture of the Earth. We are in the northern hemisphere here. And atmospheric rivers form as a consequence of cold air being over the poles. In the wintertime, the polar air moves southward and creates these really, really large storms. Warm air moves north and around the edge of the storm from east to west. And that motion and these interactions, when these like big instabilities and these long cold tongues come down over the Pacific, they grab a ton of water, and this water in the air becomes these atmospheric rivers. And that's what I have outlined here in green. And so these atmospheric rivers will follow this wavy motion of this cold air that comes down from the pole and then gets trapped, and then the warm air gets trapped and everything condenses, and that's why you see that really, really long, narrow band of potential rainfall. Okay, so that's kind of a high-level conceptual thing. Let's actually see what this looks like in action. So what I'm showing here is an animation from NOAA. The colors here, the dark red and purple, are the potential rainfall, similar to the same figure I showed before. Along the equator, which is down here, this is this sort of east to west motion, and that is pretty typical for the planet. And when you look slightly north here, what you're going to see is actually this moisture that is moving across the Pacific gets caught up and moves from west to east back toward land. And these are the atmospheric rivers that we will be talking about today. And you can't really see this here because right now we're just showing moisture, but these things actually get caught up around these like big storms that deviate down. Okay, so we've been talking a lot what happens over the ocean. Let's briefly talk about some implications of these winter storms and connect them to some regional climate. So I know this is a lot of words, but one of the things that we often see in the news is that sometimes it's colder in Texas than it is in Alaska. And so this is a headline or a picture from a news article in 2025 showing that San Antonio was colder than Anchorage. And so I actually want to just quickly move over to this. This is an image of the Earth on that day where this news article was published. And I have a green outline right here, right at Anchorage. And you can see, this warm air coming upward. And now if we skip down to San Antonio, which I think is right around here, you can see that it's a balmy minus 2.2 degrees Celsius, which is something like 26 degrees Fahrenheit. In Anchorage, it was 1.6, which is about just over 35. And what is actually happening here, if you zoom in, these motions show the wind, and this is actually wind moving southward, coming from these really, really cold areas. And then if you zoom back out, again, you can see this wind moving northward, going toward Anchorage. And so this is exactly the type of system that we see. Okay. Atmospheric rivers along the West Coast are also really important in reducing drought. They are really important in drought mitigation, and they can reduce drought really, really substantially. Okay, so now that we're all familiar with atmospheric rivers, how they set up, and some connections to regional climates, let's talk about how we turn our tank into a planet. So this is a picture of a rotating tank. Our Lego motor is over here on the left, and the tank is here. First, we have a Lego motor. This rotates the tank like the Earth rotates. We connect it to a turntable with an acrylic tank attached. This allows us to pour water into it. Now we use water to simulate the atmosphere, and you can think of the atmosphere as a fluid. So water also being a fluid is a really, really good substitute here. And then finally, we put a cold can of ice in the middle to simulate the pole. And so in our setup, you can think about this as looking top down on the planet, where this cold can of ice sits right at the North Pole, and this outer ring right here at the edge is the equator. And if you're not convinced, you can actually overlay a planet on here. So looking straight down again, this is the pole, and this is the outside. Okay, so I want to take a quick second here to talk about how this relates to both middle and high school and GSS before we get into the experiment itself. Now, I know everybody's probably seen one of these before. I'm not going to read everything on it. I figure you're all familiar with what these look like, but we wanted to really highlight this specific NGSS here. And I'm going to zoom in a little bit. So reading it in total, the goal of this science standard is to develop and use a model to describe how unequal heating and rotation of the Earth cause patterns of atmospheric and oceanic circulation that determine regional climates. Well, DIYnamics kits are a model of the Earth. So develop and use a model. We've done that. The unequal heating and rotation of the Earth, our tank rotates, but we rotate this tank of water and we can use a can of ice to simulate the center pole. And then finally, with these two things together, we're able to simulate these really large wintertime storms that impact regional weather and climate. And as a consequence, we can also see atmospheric rivers in these. All right. So now that we are familiar with atmospheric rivers, we understand the setup, I'm going to take a quick moment to show you what you expect to see in the experiment that John will be doing in a few moments' time. So this is a really great video that's done by Ryan Lindayan, who is an undergrad student at UCLA. He has a full video here. I'm just going to show a snippet. I would highly recommend it. He's really, really great, makes phenomenal videos. And so, yeah, if you have time, I would recommend it. Okay. So just kind of reorienting you here, I'm showing a video in the lab frame, meaning that you are not rotating with the tank. You're standing up top and looking down. We have the DIYnamics kits here. These red blobs are supposed to be the warm equatorial part of the planet. And then John here is putting blue dye right next to this cold can, again, where this is the pole and this is the equator. So we'll take a second and watch. You can already see structure happening. And so what this video now does is it enters the rotating frame, which basically means that now when we're looking down at the experiment, we're rotating at the same rate as the tank. And so instead of seeing these things move around in a circle, you're going to just kind of see them take place and watch the dynamics develop. And so we have the warm air interacting with the cold water that's around the can here. And you can see these elongated, long stretches of dye, which are our atmospheric rivers. So flipping this around. Okay, so yeah. And so this is a very short timescale experiment on how these really, really large systems end up forming. And this is a similar picture to what I showed at the very beginning, where you have another atmospheric river that extends across the Pacific Ocean, and it is related back to the very first image. And if you're not totally convinced, we've overlaid the experiment with the first image here, and you can see that as this comes down, the atmospheric river actually aligns really, really well with that first dark blue band of potential rainfall, and that is our experiment. Okay, so do we have any questions before we move on to the kit build? Okay, great. Cool. So next up, we have the kit build with Bill Church.
Awesome. I'm going to switch cameras. Let's make, and if somebody could spotlight Oh, good. Awesome.
I got
Can
you.
everybody see this clearly, the kit in front? I see thumbs up. Okay. Um, and I'll just share real briefly, when I got pulled into this project, John was just experimenting with figuring out how to turn a tank. I'll loosen my camera here. Let me just. So this is the same tank that Jordyn showed in the video. And we have all of the parts of this kit in a spreadsheet so folks could make them yourself. And I think the total, John, $150-ish, if John's saying something about that. And we also want to emphasize, while we're going to show how to make this kit, it's DIY, which means if you find another way to do this, by all means, go for it. John initially used record players to rotate the tanks. So whatever works to get a tank spinning, that's the goal. What I'll show you is our latest version of the kit with just using Lego parts. And if in schools, if you're familiar with First Lego League or other Lego robotics kits, these are kind of from those kits. So we've got a motor itself and kind of a wheel and axle setup. And I've already put the axle inside with the spacers. So I'm going to put that into the motor there. Then we need, in order to stabilize this motor, because it's going to get pushed up against the edge of the turntable in order to spin it. To stabilize it, I'm just going to take a frame here. Again, I just put the pegs in already. And we'll snap that in place. And then I'll take this base, which gives us some mass, some more stability. And I'll put these together. Again, the beauty of Lego is I can design and redesign. Things snap together easily. And as Kellen has shared with us earlier, her kids, got these kits, got the instructions, and just went right to it. So our hope is that any of you who tried this out find the same ease of use. So what I'm doing now is I'm sliding this in. I've got these zip ties here placed through holes that I cut in the wall of the OXO tank, just with a heavy duty hole cutter. And these zip ties are going to pull the motor, if I can get it through there, against the edge of the OXO tank. And I use reusable zip ties because I'm always tinkering with things. And I like the reusable instead of wasting one. So that's held firmly against the side of the tank. And if I move the wheel on its own, it'll turn. But we don't want to do that because we want a nice even speed for the lab. If you have a Lego hub, again, if you have a robotics kit hanging around or another teacher in your school has robotics kits, you can power the motor with this hub, and we get it spinning. If you don't have one of these, then I recommend you work with us and we can help you make an adapter. We've got this listed in the spreadsheet, and you'd reach out to John Arno, which would connect to me. We also have the 3D printed file available if anyone wants to make their own. And this adapter takes the plug from the Lego motor and gives you a positive and a negative that, if I grab my power supply connector, I can connect up and turn the tank with a power supply, changing the speed depending on if I need a slow speed for an experiment or a faster speed. That's kind of it. Our hope is to provide instructions for things that are straightforward to do using readily available Amazon parts and pieces. Any questions about the kit?
Actually, I want to chime in right now. That is quite an improvement from the ones that I built. That is so amazing. And I just also want to chime in for people who are watching. I had my students build it in a class, and it was fun and it was hands-on. And so, just don't let like the setup scare you away from it because it's absolutely worth it. And what you just showed me is way easier than what I had my students do. So well done on continuing to work through this.
Awesome. Glad to hear. Thanks for that feedback, Kellen. Uh, and now it's John's going to take it from here, and we got the tank spinning. What do we do with it, John?
Okay, so it's psi. Give me one sec. Psi. I don't yet see. Oh, there we go. There's a little lag. Do you guys see this very laggy or no?
It's a little laggy.
Yeah, it's pretty laggy. I wonder why. What network are you on? Are you on EPSSnet? Give it one sec. And if need be, you'll just hold my computer. You know what I mean?
Yeah.
Give it one sec. Sorry. This was not an issue before. But it's fine because actually what happened was I was so busy watching Jordyn and Bill that I forgot to turn on the turntables. You can see they're rotating now. I set up 2 of them. But, and this is an important point, when you first turn on these systems, you actually have to wait a couple minutes because the water in the tank has to catch up to the rotation of the tank itself. And that's already a really important Earth science point. The planet has been spinning for billions of years, and all the atmosphere and oceanic fluid dynamics is aware of that rotation and is really important for the physics. When we simply turn on this tank, the fluid has no idea the tank's spinning for about 3 to 5 minutes. And that would be the wrong problem. So we need to wait a minute. I think you're good now, yes? All right. So maybe we could spotlight. Is one image much better than the other? I feel like the camera's still really low res. Is that me or is that the truth?
I think that's the truth.
Okay, so I say let's just go to, just hold my, yeah. I'm going to hand over my laptop to Sai, and we can kill that. We kill it. Keep things clean.
You're off spotlight.
Yeah, all good. All right. Okay. All right. So let's act like this has been spinning long enough. Has it? It needs like 1 more minute. But I still want to show you what we've got. So can we look at this one? We've got a tank, the same tank Bill showed you before. It picks up. We could take this tank and spill it out when we're done. But right now it's filled with about 5 centimeters deep of water. And then we've put, in this case, a little can we would use for paint. And we've got this paint can. We painted it white so that the color is easy to see when it's in the water. And we put a couple of weights in here. So we put some fishing sinkers actually in here and a little block of copper so that this doesn't float away. Okay, so right now it's empty. It's spinning. And let's just act like I've waited long enough and that the fluid is spun up. Might even be true. So next thing we would do, so we'd wait for it to spin up. We'd have all this set up. You add a drop of soap, bang, to break surface tension, bang. And surface tension is demolished, ruined, destroyed. Now I'm going to put in the dye just like we did before. And if the fluid has spun up, the dye shouldn't move around all that much when I put it in here. It should just sort of fall in place. So there's 1 drop. There's another drop. There's another drop. And there's another drop. Great. So we put blue. Blue represents cold. Eventually that's going to be representative of cold air near the pole. And now I'm going to put in a couple of drops of red representing warmer air near the equator. Warmer air is able to carry and contain a lot more dissolved moisture. So this red equatorial air, far from the pole, is hypothetically warm and moist. And now I'm going to take, let me sneak down here. I forgot to do. And now let me make the pole polar. Let me, that's too big. I got a big thing of ice here. And let me take it and start filling my pole. And I'm going to put in ice. And I'm going to put in more ice. I'm going to just grab the ice. I missed. Oh, no. That's not what I tried to do. I dropped the ice. Okay, pretty good. So I started one storm with a piece of dropped ice, but that's fine. And now the other thing I want to do, I want to put some water in there too, because the water thermally couples. Oh, I don't have any extra water. Okay, it is what it is. So once I put in the ice, no, I need water. So back in a second, people. That place works.
I'll just chime in here for a second. And so what John did here is instead of adding ice first and then adding the dye in, is you add the dye first, and that way you can really, really see when when storms form.
Okay. So now, as Jordyn just said, so I've put the ice in after so we can see them forming. And I added some water because the water lets the ice talk to the side of the can and you get higher heat transfer. What you start to see is as the blue, cold, quote unquote, polar air starts to move away from the cold can, it becomes dense because it's next to a cold can. And it tries to sink and spread outward. But when it does, it gets wrapped around by the rotation of the planet, by Coriolis accelerations, and we get big circulating storms. And around the edges of those storms, we see tendrils of red dye. Those tendrils of red dye are moisture-rich equatorial air that's being carried. Look at this red one right here, being carried right up towards the pole. That's an atmospheric river. And so that's a fabulous example of an atmospheric river. And actually, we formed one on each side of this big storm, actually, which is interesting. Normally, they go the other way. This one's going both ways. That's really nice. And so that red tendril around that huge storm, that actually is an atmospheric river. So the edges of these big rotating storms have these rim flows, and those rim flows, if they reach far enough down in latitude, grab moist air and carry it around and to higher latitude. That literally is an atmospheric river. When that runs into the West Coast, we get a huge whopper of a storm. Does that make sense? Does that make sense? Oh, it makes incredible sense. Fabulous. So now what's the next thing we can do with these systems? We can mess with them, which is what I love. That's the whole point of DIYnamics. So over here, this one's rotating at 5 RPM, and we got one big storm. This one's rotating at 10 RPM, which means Coriolis accelerations will wrap things even harder and you'll get smaller structures. So you're going to have a stronger deflection. And instead of one huge storm, here we should get a few storms. So let's see if we do that. So I'm going to do this again. I'm going to put in the same dye again. I might put in ice now. I'm putting in ice this time slightly beforehand to show you that it's not the end of the world, which order you do things. And you might say, actually, let's not might say anything. Let me see if I can put the ice in without spilling it this time. Boom. Boom. Up, drop the ice mist. Boom. Okay, that's probably enough ice. We made our North Pole, another dropper. I'm going to couple the ice to the can with a little water. Great. And now I'm going to put in my red out here. Red out at the equator. Boom. That's my equatorial band of moist air. And now I'm going to put in my blue. Boom, 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 boom. Okay. And so let's see what happens this time. I'm predicting that if Coriolis is stronger, we should have all the same dynamics, but the wrapping of the storms should be more intense. And therefore, we should get smaller storms, and therefore more of them will fit in the tank. Let's see if that happens. Ooh, there's what's called an amazing, there's actually a jet stream flow in there right now. A little hard to see, I think, on the camera. And that's going to then go unstable, just like what happens in the atmosphere. It's actually dynamically similar, as we say. So it's the same process. Ooh, yeah, you can see much smaller structures. Look over here. Now we have, sorry, can we go back and forth? We have a couple of huge storms over here in our slow tank. Oh, actually with a whole bunch of beautiful atmospheric rivers that we skipped. I'm a bad person. And now if we come back to our more rapidly rotating tank, you'll see they're much smaller scale. And so they're much smaller scale. And this is what would happen in a sense on a faster rotating planet. You'd have the same processes happening, but you get much more and smaller storms. And so it's unclear if these will even make it out to the equator to get atmospheric rivers around them. But if we wait, well, that will occur. And actually, do you mind if I go back here? So can you guys see that there are more of these guys? Oh, yeah. Nice side view, too. Oh, yeah. Oh, yeah. That's stunning. And so you can see the three-dimensional structure. The dye's largely on the bottom of the tank, and it's kind of tipped into these kind of cones. And that also agrees with basic atmospheric dynamics. It's weirdly similar to an atmosphere because it's got all the right physics. A pole to equator temperature gradient and rotation, kind of what you need. Like literally, that's the fundamental physics. And so we're getting these storms. Oh, they're growing. Ooh, so nice. So if you guys see, while we're at it, we're just having a good time waiting for these to grow. There are some holes in the dye. Do you guys see those little kind of scallops in the dye? Anyone? Scallops in the dye? Am I the only one? So the scallops in the dye are because this is a different process. It's because actually the water in the tank is evaporating. And as it evaporates, it cools the surface waters, and those sink down in little tornadoes. And so that's a different process. I can never turn that off. But that is not something that typically occurs in the atmosphere. It does happen in the tanks. Everybody thinks their tank is broken. Their tank isn't broken. It's exactly what should be occurring. It happens in Earth's core. It happens in stellar interiors. We just don't typically see it in Earth's atmosphere. We see this polar instability much more. Okay, they're just getting to where they might run into the red. Come on, baby. We gotta wait. We're getting there. Come on, red. I don't want to throw any extra red in. If I spritz it in at the end, it'll add its own dynamics. I want to see some of the red get caught up on the storms and get wrapped around their rims, because that is what happens in an atmospheric river. Come on, rim flood. Oh, it's so hard to be patient. Ooh. Okay. We're just starting to get interaction. Just a couple of purple bands where the red is interacting now with the storms. Come on. Anyone? They're getting there. And so, humbly, I will say this one's taking a little bit of a long time. Maybe I should have started them at the same time. But when you run a couple of these at once, what I like to do is I set a couple of these tanks up and have every tank be a different rotation rate and let all the students describe and try to interdescribe how do the tanks create different results. And so then it's really interactive with everyone describing what they see. Oh, wow. I think they side, just so you know, that's a zigzag instability. See that?
Wow.
Oh my God. That's the second time I've
Really?
ever seen it. Yeah, that's a zigzag. Look at that. Sorry, I'm not trying to change topics, but that's like a classic, relatively new instability found in
That's
rotating
awesome.
stratified fluid dynamics in the oceanography community. It's only like a 20-year-old. It was only found at the start of the 2000s, and we're getting it in like a $20 tank. That's amazing. We're all so lucky to be doing this webinar today. I'm shocked, actually, that occurred. Okay, so, we're starting to finally get rivers. You guys see that purple extending around the edges of these storms? That purple is the red interacting with the rim flow on these smaller storms, and it's forming again that classic structure where it's pulled around and it's starting to head up to higher latitudes. You guys see it? Anyone? Anyone see it? Anyone? Anything? Anyone? Okay, Kellen's giving me the positive sign. So we're starting to see them there. And now let's go back to the slower tank that's had more time to develop. And again, we see these huge, much bigger structures now. And they've really wrapped the red all around. A lot of the red's been brought up to high latitudes. And again, that's what underlies the idea of an atmospheric river. While we're at it, we're going to do one last thing because we're having a great time. I'm going to take out the can. I'm done with the experiment. So now I'm going to take out the can. If I take out this can, what should happen? Can we see a new piece of physics? And the answer is, well, I've got this spinning fluid. And if I suddenly create a vacuum, it's all going to go in. And if it goes in, well, it should spin up to conserve angular momentum. So hopefully we'll see a big vortex that spins faster than the tank itself. Should we do it? And the answer is yes, because either way, we're doing it. So ready, set. And let's see if we can see it. Oh, we made awesome waves. And we also made, come on, grab some dye. Right now it hasn't grabbed any dye, which is demoralizing. Should I do it? A little dye. I'm going to add a little dye to it. And we made a big vortex right there. And what I want to get across here, amongst other things, is that one, there aren't very many rules for these systems, and two, giving your students a little dye and one of these simple kits lets them play with a lot of really crazy science that they don't normally get to play with. They get to see vortices, they get to see turbulence, they get to see, in this case, a little Jovian style vortex. We made this big, nasty, great green spot. It's easy to make and it's super fun. And we can talk all day about what the heck's happening in there. Let's go do it on the other side too, because we just love to tear out the center of the Earth. Here again, we're pulling off the North Pole of the Earth. And let's see if we get a vortex. Oh yeah, slightly better vortex. I'm still going to zip across. And if we could rip off the North Pole like a Band-Aid, that is, of course, what we would get on Earth. Interestingly, we do get huge polar vortices on Jupiter and Saturn. And actually, I've got a tripole forming here. I've got a vortex next to a vortex, and maybe this will be a vortex too in a second. And that's called a tripole. And we see this in the ocean. We see this at the poles of the gas planets. And okay, after we're done with atmospheric rivers, then you just start playing. And I think that's one of our key points. Bill and Jordyn have been arguing that forever. This should be really fun. Learning should be fun. And these are incredibly enjoyable systems. I want to do one more thing and then I'll shut it. I just want to make a little mechanical turbulence. Might as well. Let's get a top view again. So, this is a question I always get. What happens if I put my hand through there? I like to just use the quote-unquote tool. Let's inject turbulence. Let's make a mess. Oh, I just totally ruined everything. If I put in a bunch of turbulence, if I make fluid motions faster than the tank, then the fluid doesn't really know it's in a rotating system. But then it slows down after a while. There's a little friction, and these velocities slow down. And once they do, I've suddenly made massive rotating turbulence like on Jupiter. And that is the most delightful thing. These are fluid spinning tops now. It's really turbulent, and yet it doesn't mix like a non-rotating fluid. That's the fluid dynamic you see in the ocean, atmosphere, and again, on all the gas planets, all the big planets. So lots we can do, and then when we're done, we just turn it off, and it goes away. And the minute we stop rotating, all this physics is gone. So thank you very much. And if you guys do have any questions, we would love to chat.
Go for it, artist.
Hi, can you hear me?
Yes.
We're good.
Okay, so this is really cool. And immediately my brain is going to what's happening in 3 dimensions. And we for many years have done convection demos with blue and red dye in tanks. This is more like looking at a top-down view of the dynamics. But with 5 centimeters of water, is there enough to see a 3-dimensional interface?
Should I take that one? So yeah, so another one, I was going to do one other experiment, which is what happens if you don't rotate? And if you don't rotate, then you do get to see a classic downwelling away from this center cold patch. And then it downwells, it spreads all the way out, and then it comes all the way back up. So it's a big, in this case, a big axisymmetric circulation. And you can see it even in a 5 centimeter tank. And then you rotate it and everything changes. It doesn't really want to overturn. Everything wants to be actually a little local fluid gyroscope. Everything kind of stays standing up and you get these axially aligned storms, which is just totally different and a different way to transfer heat than you get in a non-rotating planet. So Venus is very different from Earth. And yeah, you can see that even in 5 centimeters, but if you want, you can always go to 6 or 7. Does it make a big difference? No, it's already enough.
And John, don't we also have a thermal wind experiment where we're looking in from the side?
Yep, we have one experiment where we just look from the side and you get to, again, see how things overturn. But that's a different one than this. It's related, but it's slightly different physics. You see it better at slower rotation rates, which we can also do with the same system. Those thermal winds are what you see in Earth's jet stream. So you can do jet stream experiments as well. And it's cool because jet streams also, people go, what? I just hear about that when I'm listening to the news. And the answer is, nah, you can just make it. Tank can be 30 centimeters across, make one.
So how do you pick out a jet stream in the tank versus the thermal rivers or whatever you call them?
Yeah, so the atmospheric rivers are these specific thin little filamentary structures that wrap around the edges of these big storms.
Yeah.
Those storms form every winter in each hemisphere.
Right.
And around the edges of them, we often get these atmospheric rivers. So as Jordyn said, they're roughly 5 to 10 forming at least per year. And each time you just carry up all this moisture to high latitudes. In contrast with a jet stream, in the winter you have this big cold patch of air up here at the pole, and under some conditions it basically stays there. The fluid just wraps around that cold spot, and so when it wraps around that cold region, that's essentially the jet stream. It's air wrapping around the cold part of the planet. Yeah. Oh, thank you. Yeah, it was in your slides. Take it, Jordyn. Oh, very nice. Yes, and so that's again just a tank, that's that white tank. And we're now rotating much more slowly. And when it's really slow, you don't actually get the storms. The dye just wraps and wraps and wraps. And the fastest flow is at the top of the tank. And that's just like what happens in the atmosphere. The fast flow is at the top of Earth's atmosphere, right where our planes are. So we go really fast when we're going west to east and slower when we fight the jet stream. And you're creating that. And really, it's a nice analog model.
And if you're interested in running something like this in your classroom, we can give some advice on how to get these to work out and things like that too. And we have some experimental designs that we're happy to share.
Yeah, I'll chime in for that one. I did upload an attachment to a worksheet that I don't want to take credit for because I must have adapted it from something, and I want to make sure the person that I adapted it from gets credit, but I cannot find who that was.
Oh, I think it's Juan
Um,
Laura. I think Juan Laura, who's now at Yale, he made that
okay.
when he was at UCLA. He made a bunch of great stuff, and
Yeah, it is
I
really
think he made
awesome.
the first version, but then you made super nice changes to it. So
Thank you. Yeah, and it walks the students through it, and I teach this in my block period, which is about an hour and a half, and so it allows for the setup, and it really just becomes a work at your own pace, and you end up moving from group to group and just answering questions and playing with it one on one, and it is definitely one of the most popular labs in my class.
Kellen, can I ask a question? How many of the tanks do you have then in your classroom?
About 20. My biggest classes are about 40. My school is also blessed with a budget, so I bought 20. So they work in pairs.
Okay,
Yeah.
that's really nice. John, I have a question. And so couple things. One, have you played with using warmer water or like to try and increase the temperature gradient?
you can do warmer water. Yes, you can play with just about everything.
If you
Um,
did that, would you put the warmer water? Could you change the temperature of the like? Could you pour some warmer water on the outside?
Done it. So, yes. So, one
Does
thing
that
we
make
did
sense?
at one point, which was really fun, my friend Bob Ecke came to visit and he built a little dam around the outside, filled it with essentially boiling water. Basically used a teapot. This was super hot water. This was ice water. And he just
Mhm.
got these incredibly intense storms. So,
Wow.
he cranked up the pole to equator temperature difference
Yeah.
and you get what you'd think you'd get. And so, that's the joy is it's not very hard to come up with, well, what are the ingredients we should play with? Temperature and rotation rate. You can also play with fluid depth, and they're all easy to play with. I usually leave the depth fixed, but yeah, usually I just kind of leave that one be. But you can play with it, and that also changes the size of the storms. The deeper it is, the bigger the storms. The bigger the temperature gradient, the bigger the storms. And the slower the rotation rate, the bigger the storms. And the rotation rate, that makes sense because the faster it rotates, the more Coriolis wants to wrap things into a tight circle. So the faster you rotate, the more these contract. The more you force them with temperature difference, the more you try to drive flows, the bigger they get. So the temperature difference kind of forces the fluid to move, right? And Coriolis deflects it off to the side. And so they're just always fighting. And
Can
so
you
you can really predict this stuff with your students.
um so I don't so can you represent sort of like the Hadley cell movement here or no?
It is, you can do a Hadley cell. So the Hadley cell is if we don't rotate and we just put a cold can at the pole,
Hmm.
then you really are doing a Hadley cell, right? If you want, you can put hot water out here, but it doesn't matter. It could be warm water, room temperature water. And what'll happen is this sinks, and because all the fluid next to that cold can is now suddenly cold, polar, dense air.
Right.
And so the stuff out here relative to it is warm and it rises. So then you get rising here and sinking here. Jordyn, do you want to talk? Jordyn also uses a linear tank and then
Yeah.
put cold water on one side and warm
That's
water on
right.
the other.
Yeah.
However, if you rotate that, uh, it does well. Actually, that's really fun too. You can rotate that as well and also make all these interesting structures. But in here, it looks like an atmosphere when you rotate it, right?
Mhm.
And really, the Hadley cell is axisymmetric, right? It's not really a channel. It's actually happening everywhere.
Mhm.
And then you
If
rotate it, and the Hadley cell breaks apart into the storms that we actually see in our atmosphere. We don't have a global Hadley cell, right? Venus
Right.
does. We don't. Why? Because of rotation.
if you also rotate the rectangular tank, so I use a rectangular tank for Hadley cell, and you can either just put ice on one side or hot water on the other. I've done both before. Um, you can layer, if you use hot water, you can mix a little bit of dye in it, put it on the top, and then you'll actually see it move across the top. And then the cold water on the other side, you can see it sink and then rise. But if you rotate it, you'll actually get jets that form on either side of this like rectangular tank. And so you can see those like jets as well in that type of experiment.
And so in a way, you're making trade winds and westerlies when you do
Yeah.
that.
Mhm.
I like that.
And one thing we'd love to offer for this group and for a group that might watch the video is to reach out to us. We don't want this presentation to be something that sits out there and great, go do it. You're on your own. We want to grow a community of people that are working hands-on with these kits. I say our kits, but really any rotating system that you can make work. To take those standards that Jordyn showed and do that with a hands-on experiment rather than a video, or there are great computer simulations out there, but it's fun when you can get your hands wet.
And it's fun when it's in the hands of students. I've seen this.
Yeah.
I use these in all my classes all the way up to grad level. And it is just what Bill said. When you actually have people doing hands-on, it's a rather different interaction.
Mhm.
It's funny, I have less kits than you do, Kellen,
Mhm.
but I also don't have 40-person classes for this stuff. I usually use it in about a 30-person class. And I think I have like 10 kits. And we often use just like 6 or 7 actually. So it's like groups of 4 and 5.
Yeah,
And that's
I bought enough for pairs, but
I
they
know
they
I
kind of
like
work with
pairs.
the people. Yeah.
When I can do pairs, I do, but when I can't, it doesn't really
Yeah.
fall
What I
off.
liked about mine too is, some of my batteries started to die, and so some tanks were rotating slower than others, and that was really cool. Students were running around the classroom, like looking at the different structures that were made based off of the rotation velocity.
Yeah. Well, so that's what's nice with the newest kits is you can control velocity with this power
Yeah,
supply, and
that was
that changes your world a bit, for
And
sure.
the other thing, and I don't know if this will work here, but actually let me reduce
Yeah.
this size. So we also took a ball, put it on the edge of the tank and ran it with a big light in a dark room,
fun.
and the camera looking at this ball going around, we get the sun, earth, and moon.
So you put a camera on the other side of the tank.
So put a camera on the other side of the tank, aimed at the ball, with a light over, say, way over on the there, and you can get phases of the moon.
That's pretty cool.
So John and I and John Jordyn and I are realizing, because we're so soaked in fluid dynamics, that if we dry things out, we can do other physics too,
Hmm.
or other other earth science. We can do exoplanets that are go in front of a sun or a star rather. So it's a rotating playground.
Yeah.
Awesome. All right. Well, if there's no more questions, we'll close this up. And I'll remember to share my screen this time. All right. Share and uh-oh. Share. All right. Yep. All right. So those were the first couple of slides, just introducing you guys to the webinar and what NESTA has to offer and everything here. And shout out to our presenters who did an amazing job. Our next Earth Science Education Hour is coming up really fast on Tuesday, the 24th, 6 to 7. It's called Notebook LM, what it is and what it isn't. And it's really awesome because it is a collaborative webinar between NESTA and NAGT, and it's free. So register now, and hopefully we will see some of you there. And here is just a thank you. And if you are interested in more Earth and Space education hours, you can scan the QR code. And yeah, thank you guys all for showing up, and reach out to any of us if you have any questions. I've taught it in a high school class. They teach it at different levels, and we're all here to support you in any questions that you may have. All right.
Thanks, everybody.
Okay. And there we go. All right. I do not know how to get out of this. I'm going to stop the recording. Oh, I know how to do that.